Okay, I believe we can start. Welcome to our talk, Fix First, Investigate Later, how an eBPF rollout brought down our network. First question is for you. How many of you were affected by production outage last year? Please raise your hands. Okay, great. Now, second question. How many of you, it was caused by something in your cloud provider infrastructure? Just raise your hands. Okay, thank you. In how many cases it took longer than 30 minutes to be mitigated? Okay, longer than 1 hour. Okay, longer than a few hours. Okay, longer than 1 day. Okay, I believe that we are in good company. We would like to walk you through how one incident hit us hard, and more importantly, how we deal with that. So, my name is Grzegorz Głąb. I am a cloud engineer and whatnot, working mainly with cloud infrastructure and reliability.
And I'm Zain Malik, working at Exostellar as a principal software engineer.
But our story started at Cloud Kitchens, where we both were part of the core infrastructure team.
Yeah.
Okay. So at Cloud Kitchens, we are part of small infrastructure team having like 6 people. And we are managing a large-scale Kubernetes clusters, so thousands of nodes, tens of thousands of pods, and supporting the whole company infrastructure.
But first, let me take a walk through like what we are going to be covering today. We are covering through like some small kubectl commands, get DaemonSets. Then we'll go through like some mutation webhooks, how to write them, CPU sets, and go into the details of eBPF kernel to user space data transfer. Now you might be asking, like, why all of this technical like deep dive just for an outage? And that's a good, valid question. To take you to more of that context, it's like over the years we learned how to operate that way. Usually when the outage happened, in our case, it was like So usually when we were having any issues, like it would pose a risk to the business continuity. And when that's happening, things try to escalate pretty quickly. And our team naturally becomes the last line between the support, between cloud providers and the whole org. Now, the support orgs do their best job. Sometimes they can reproduce the issue and they will call it like which workload introduce it. But on the other hand, we have to play on the both sides. We have to find issues in the cloud provider infrastructure, but we also have to find issues in the workload that the users are running into. But in most cases, we have to do whatever is absolute necessary and go as deep as necessary to fix the issue, to continue with the business continuity. Without any further wait, let's hear the Grzegorz outage story.
Okay, the outage. So what actually happened? One night, one of our teams called us saying that the network is broken. And I was on call that night. And as you may know, we don't have a generic runbook called network is broken, so I needed to start investigation from scratch. And actually, when we look at the cluster, we noticed that on 50 of our nodes, we have degraded network throughput. I mean, most of the throughput were limited to 30% of the previous speed. And it was causing an application, on the application layer, it was causing a context timeouts. And the team asked us, hey guys, did you introduce any changes recently which could cause that? And actually, the only change which we did was to update Kubernetes control plane. And when we upgrade control plane, as all of you may know, we follow the procedure. We check what happens, we check for API compatibility, we check deprecation notice, and we first do it on the staging clusters. And usually it is a smooth process. We know what we are doing. But in this case, there was something new. We noticed that new DaemonSet appeared in our cluster. And what was this DaemonSet? Actually, it was a pretty cool observability toolkit for network called Retina. It was part of the control plane metrics feature in AKS. But in our case, we were wondering, because it's supposed to be eBPF, low overhead, so how it could cause this kind of network degradation. But during an outage, you need to question everything. So in this case, we had a priority, just restore our business continuity. So in our case, it was meaning that we need to fix somehow those context timeouts. The other team was actually doing mitigation on their side, And our play was to investigate this network degradation. And of course, the first thing which we tried to do is to delete this DaemonSet. Obviously, it helped for a short while, but it was recreated. So we needed to use some kind of another approach here. So let's go back and revise how API server handles requests. Each write request, like create, patch, update, go through different phases. And as Kubernetes was built with extensibility in mind, we can hook up into some of the phases. And I'm talking here specifically about mutating and validating controllers. In our case, let's take a look at mutating controllers, mutating webhooks. It allows you to modify the object before it's stored in etcd, which is more important, it does that without modifying the object resource version. Why is that important? Because all the controllers watching resources usually react and trigger the reconcile loop when the resource version changes. In this case, it didn't happen, and it was our entry point to mitigate our outage. And our idea was simple. When you look at Retina DaemonSet, you know that DaemonSet selects the nodes on which the pods needs to be scheduled. And Retina, in this case, was using match expression term, which consists of several conditions. Each of these conditions operates on node label. So our idea was to add one condition which could never be satisfied. So in the result, we have a DaemonSet which doesn't span any pods on any nodes because nothing matches. So as we already had one mutation webhook, we thought that, hey, let's just extend it. So we did the code part. We added a new handler which was modifying the object. And we extended our mutating webhook configuration with a new entry, specifically targeting DaemonSet with the label Retina and create, update, patch operations. Of course, we tested it on our kind cluster, and it was working fine. So when we deployed it on staging environment, of course, it wasn't working. And when we took a more deeper look, it seems that it wasn't even invoked. When we inspected all the configuration, it seems that our mutating webhook configuration wasn't looking the same as we thought it would be. Actually, it has a new entry with namespace selector, which was excluding object in some namespaces from being mutated. It was unexpected. But it appears that it is a protection layer in AKS. They have a special controller called admission enforcer, which role is actually very, very good. It's supposed to protect users from changing the object in system namespaces. It's to avoid, risky changes. But in our case, we wanted to do it. So what were our options? You can, of course, disable it. When you add a label or annotation, we choose label, it's supposed to be suppressed for this given mutation webhook configuration. Of course, we took a step and deploy it. And unfortunately, again, it didn't work. This time, it has the label to disable it, but the namespace selector part wasn't removed. At this time, we didn't want to speculate why it could happen. We just did one simple thing. We delete this mutating webhook configuration entirely, and then just reapply it. And this time, it worked. It just looked exactly as we wanted. Later on, to not repeat the step on every cluster, we use our CI/CD first to delete this resource from every cluster, and then recreate it. And later on, when we were inspecting why it happens, it was because how field manager works in Kubernetes, because our CI/CD wasn't introducing those fields, so it wasn't also removing them. And of course, when we deploy it on all our cluster, the one thing which we need to do was to trigger the reconciliation and mutation loop by just putting a dummy label or annotation on the Retina DaemonSet, which actually resulted in restored network throughput on our node. So now let me give the stage to Zain to explain about the investigation part.
Wow. Thanks, Grzegorz. So now we have disabled the DaemonSet, bandwidth return to normal, context timeouts and cancellation stops. So basically, we are back to business continuity. So this is just show like how far the platform team sometimes have to build complex workarounds to just keep the lights on. The fix first part is done of this presentation, and now the investigation begins. Of course, we did what we have to do is like open support issues to the cloud provider, open the issues in the GitHub also. And it looked like on all the benchmarks that they had, they could not reproduce either the issue or this was not expected. They were putting the blame on our workload back again. Now, at this point, as an end user company, the investigation is just a personal engineering endeavor. There's no immediate business value to provide or custom value to provide by this investigation, any KPIs to improve. It's mostly like as engineer, we need to root cause for build better understanding. And that builds intuition for future incidents. That's how we built in our team from the past incident. So we went ahead and tried to do, maybe it's very simple. Let's try to reproduce it. We built up a small cluster with a 4-core nodes machine, install the Retina DaemonSet there, and run some iPerf test. And we were hoping that it's going to be something super obvious that we will figure it out and just report it back. But guess what? There was no degradation, actually. It behaved totally different from the production environment. And there was using the, we are calling it a lazy test because that's the effort we put. It was very lazy initiative. And now, at that point, what we have to do as a platform engineer, step back, look at the workloads, look at the environment that was happening there, and try to reproduce exactly the issue. The lazy approach is not going to work anymore. We step back to the incident. We had all the metrics. It was, as Grzegorz said, like affecting in that cluster 12% of the nodes. It was not all the cluster affected, right? 50 of 400 nodes were degraded. And there was something common there, like there was a high-intensive network workload there was running. And all of them were high core count machines, specifically E32 and D32, right? Now we had a pattern. This was not random. So we had to try with this pattern again. Another thing that was happening was like the workload was receiving the traffic on multiple threads. With the iPerf, you might know that like in the client side, you can do concurrent requests, but the server has to run on one core at best. So it doesn't perform the same way. So we have to mimic the workload behavior that was in the production. And we were like, let's go and try this again and roll out the Retina DaemonSet in that environment. And yeah, it worked. Now we had the network throughput drop significantly from 8 to 4.5 gigabits. That was 44% performance degradations, nearly cut in half. And that was even worse than our production environment. That was the biggest win, because now we have a controlled, reproducible environment, and that is like half of the win. Now we can do it as much as we want, iterate on that, try to look how things are working, do deep dives, like what is actually limiting that. As a platform team, first we did was like look at the other metrics, how we would advise users, because users would come to us and say like they are not getting some performance, and it was like, have you looked at throttling? Have you looked at the context switches? Have you looked at other? So now we were doing the same thing with the Retina. And of course, the first thing we saw was the throttling. It was very clear that Retina had standard resource limit, very conservative values, which seemed reasonable for normal use case, and it was being deployed by cloud providers, so we did not have any way to configure them. And our first hypothesis was established. This is the CPU throttling. Like we need to stop the CPU throttling. How we do to test it out with the user workload, what we recommend them is to remove the limits. Let's run the workload. Let's see how much CPU it actually needs. This will help us know how much CPU cycle it needs to perform in a normal way. We just went ahead, remove all the CPU limits, and let's try it. And actually, it got worse. Like it got worse from 4.5 to 3.7. That was additional 18% degradations. That are our first major, like, wait, what is going on? We don't know what we are doing. Removing constraint made things worse. And this was defying our mental model of how it's supposed to work. But lucky for us, we had a good observability, and we were able to see on the next panel or graph to complain what is going on. Yeah, we found it, context switches. After unsetting the limits, like they were off the roof. That was not a simple resource problem. We knew like it was using multiple cores, and now we are in the multi-core behavior, typical. At this point, how we recommend our users will like, when they are having a lot of context switches problem, is like to evaluate CPU sets. For those who you don't know, CPU sets is the Kubernetes way to actually pin a CPU to exact containers. So that will it's like using the policy, CPU manager policy static. Most of the cloud providers, Kubernetes distro already support that. It's just a kubelet config. You have to do it. You can do a simple kubectl, check if the CPU manager policy is static. Now our hypothesis was like we have to remove this scheduling jitter, and we have to remove these context switches. That was our first experiment again, after with one dedicated core. We'll set the limits to 1 core. You'll get 1 pin core, and we'll see what happens. And actually, it improved. It improved to 5.2. Now we are going somewhere. We are like more optimistic about like our experimentation, but it's still way degraded than the baseline. Better than before, but our logical next step was like, yeah, we need to double it. We gave it 1 core, let's give it 2 cores. And follow with this working path, maybe we'll get into some place where it's not happening anymore. We doubled it, and it went worse again. Like now, this was again like this was happening, the performance was worse again, and more cores were not the solution. That was not the path that we would have to take. We needed to understand Retina's behavior. We need to dig deep into the code, what actually Retina is doing. And during this experimentation, we also discovered another pattern. In different kind of nodes, when the number of the cores were increasing, the performance was even going worse. So we did experimentation with 32-core machine, but when we moved to 64 cores, it even got worse than what we had in 32 cores. Now we had a pattern. Like we knew like on more cores, it's performing really bad. Knowing that, we moved now towards the Retina. So how Retina is like an open source project, really cool observability toolkit, and it's built around plugins. It works for Kubernetes networks, and there are multiple plugins for network stack from DNS forward, flow tracking, and different eBPF programs which can capture events. What we did was next was like, let's try to randomize that. Let's try to enable and disable all of these plugins, all at once, few, enable 1 or 2. With all this randomization of this enabling and disable, we discover like the ideal setup was if we disable the packet parser. If we disable the packet parser, like we were really actually close to the baseline. And now we knew what was the culprit plugin. Still needed to understand why. What was packet parser actually doing? We knew with the number of cores it was degrading, but we need to understand still what it's doing. So what is packet parser doing? It's captured all the TCP UDP packets at the ingress egress points for the pod and node level, right? And it's also do pretty deep parsing of the packets, like extracts IP, port, TCP flag, sequence numbers, TCP timestamp, everything needed for observability for network. And also it's generating like Hubble compatible flow events. So you can actually use the Hubble, which is really great. I also have the metrics foundation, so it will inject metrics of latency, throughput that you can see, or even do the TCP state analysis through the metrics. And optionally, it has also connection tracking via contract. But that was optional. It was not enabled. Now, this is great, but we need to draw it, like what is going on here and how it's working, because still it's very high level for us to blame into one of these parts, like which packet parsing is doing and what is going on. That's where we start jumping into the more what part is running in kernel space and what part is running in user space, right? In user space, we have a 10K buffer channel, right? And one producer. This is very common in eBPF toolings. And we had 2 consumers that were consuming from the producer. On the user space, it was like perf read, blocking I/O, right? It would destroy the packet struct, convert to flow protobuf, add pod or Kubernetes, any kind of metadata from the API. And like it also had like even distribution to latency, like packet forward, TCP flags models also. Now moving back towards the kernel space, we see there were like 4 TCBPF programs, right? And they were specific program names. Like we already know that there were 2 for the pod ingress and egress, and 2 for the node ingress and egress. But what called out was like the 32 pages per CPU performance perf buffers. It's the perf arrays. That was like we start digging into like what is this? Like what is happening at per CPU layer, right? And it is like how it sounds exactly. It's on for each CPU, it will add a perf array. So the perf array architecture is like will have a separate buffer for each CPU core, and it's supposed to work with scalability, right? With more the cores are happening, from the user space, it will have to pull all 32 separate buffers. It must maintain a first in, first out order across all of them, constant jumping between CPU-specific data structures. It can create a massive overhead as the number of the cores grow. which looks like exactly like this. In a low-core machine, the overhead is not that massive. But with each CPU getting its dedicated array, like user space consumer had to read all the arrays. This cache contention and memory barriers will look like pretty much the culprits for that. So it was pretty expensive to do this 32 structures check. And the first question was are we the first one who are discovering that? Cannot be, right? Yeah, we were not. We were not. It was actually such a known issue that Linux did a re-implementation in the kernel for eBPF to replace this implementation with the buffer rings. So the old one, due to known scalability issue, the ring buffer was shared across, new implementation will be shared across all CPUs. Now we did not have 32 separate per CPU arrays. We had a single unified structure. Any CPU can write directly to this shared buffer. It had a brief spin lock only during space reservation. And actually, the commits are totally lock-free. And user space monitoring is just one buffer. Now, the performance win we had is it's going to poll once and not 32 times. And data stays in the cache where it's running. And way less memory traffic, concurrent writes without locking. And actually, ring buffers were added exactly to solve the scalability problem we discovered. Now, being the engineers we are, we had to do one more thing. Just go ahead, fork the Retina, and change the implementation. The implementation, how it's done, it's already ready for the migration, because when it was introduced, the ring buffers were exactly introduced for it to be able to just a simple swap. It does require some additional implementation changes. This is not all the changes, but just for the simplification, this was the main change. Now, only one thing had left to do, we have to rerun our benchmark test, right? Same setup as before, 32-core machine, same workload conditions. Time to see if ring buffers can actually deliver on their promise. Let's take a look what happened. We're back to 7.4 gigabits per second. The baseline was 8, and this is pretty I would say normal observability tax we have to pay. To put things more in context, without Retina, we were at 8, without any observability. With Retina, with CPU set tuning that we did for one core, we were at 5.2. The default settings were bringing us to 4.5, actually. And eBPF ring buffer, we were at 7.4. Now, this is not an outage. This is everyday observability tax, and we can live with it. So what would be our recommendations, if someone is listening and they're building eBPF tooling? Yeah, please support both, because we have not tested all the use cases. There might be configuration that might work better for perforates, right? We are just trying to solve an outage in our case. We don't want to say there's a universal winner, even though in our case, the ring buffers were outperforming the perforates. And we are advocating for choice. So as a platform engineers, we can choose if we want to run with perforates or the ring buffer, depending on our workload, because if you're going to offer it to the all kind of different workloads, at least the data and deployment reality drive the decision. I think we are slightly over time, so let's go with jump to the conclusions. As we wrap this up, I think there's some key takeaways here. To bring this all together, fixing first has to be your priority when users are impacted. Know your platform deeply, understand which knobs are available, like mutation webhooks for instant configuration injection to disable a DaemonSet, and investigate later to uncover those systematic issues that can be fixed during an outage, actually.
And Kubernetes ecosystem gives us incredible flexibility and extensibility. We just need to know how to leverage it when it matters most. And when you are during an outage in the middle of an incident, stop the urge to start debugging immediately. Just step back, look what changed, try to mitigate first, and later dig into why. And I believe this is all what we have prepared for you. So now it's the time for the questions. So.
Yeah, and we will in the KubeCon, so please stop by the booth at 5:42. I will take any question we. Yeah.
Yeah, and if you find me over the KubeCon, just come on and talk. We can also.
Yeah, let's go with question. Yeah. Okay.
How did you decide 8 meg was the right size for your ring buffer?
We didn't know, actually. That's a really good question. We tried with 32, it failed. It was panicking at kernel level. We tried with 4, it was not the ideal. We settled on 8. That would be the right configuration also to give it to the users. You're right. Yeah.
Once you narrowed it down to the packet parser, how did you actually, did you use any tooling to investigate the eBPF programs in the kernel? Or did you just look at the Retina code that was open source? Or?
Yeah, we use the tooling for the BPF maps, to see the actually perforates, but this was not actually telling us anything. There was a lot of perforates. Does it mean something or not? That was not, we were not able to tie it. But it was very clear the perforates were there, and also the context switching was happening a lot on those cores. Yeah.
Thanks for the presentation. You mentioned that the problem was that with perforates was aggravated as the number of cores increased. The Retina project didn't have such moderately sized 32 cores machines in their CI pipelines to test on.
Yeah, so actually we reported the issue immediately, both in Retina code in EKS, and from the answer, they couldn't reproduce this issue, and they promised that they introduced some performance into the CI/CD, but after a few months now, we didn't get any update on that. So,
but I think the takeaways here is not just limited to Retina. It's all BPF toolings. There are many. I'm not going to name all of them one by one, but most of them are still using perforates. The Cilium is the only project that has moved on to the ring buffers, and you can say that they know what they're doing. But many other BPF tooling, at least the one we are checking, are still using perforates as for today.
Hello. When you write in the ring buffer from the kernel, the user level process wakes up, and this causes some extra CPU increase. You can you can try to minimize this, but not waking up on each message, but still there is some noticeable CPU increase. Have you realized that or not, has the CPU consumption of your program increased?
Yeah, so in that case, as we were using CPU sets, that's what I wanted to say is in our case, it was enough, right? So that one core was just dedicated for the user space, and it was able to poll without any problems, and we were able to do that. Probably if we go to 2 cores, it's going to happen again, the issue. Yeah.
Did you ever track down what the initial change was that caused the degradation? Was this Azure deploying Retina for the first time, or did they deploy an update to Retina that introduced this?
Yeah, so actually we were enabling the cluster control plane metrics feature on Azure. And at some point, I believe it was updated from 127 to 129 of control plane. It just brings this Retina set alongside. And I believe that in the beginning, you couldn't even disable it. After we started the issue, they believe they added some knobs so you can opt out for it. But yeah, at that point, it wasn't possible.
Thanks for the talk. One thing that I was interested in just clarifying, so you mentioned that with low core machines, you had no problems, and that even with the solution that you came up with, there was still some overhead that came with the observability tax. Did you see that similar scale, that amount of degradation in lower cores too? Is this something that grows with increased CPU counts, or?
Yeah, I think the issue with that, the cloud provider, when they're providing low count machines, the network cards that are attached are very low. So you cannot actually take them for a performance spin. If it's 1 gigabyte per second, the network card, 4 cores are more than enough. So you really need to go to 10 gigabytes per second, and that is not available with low core machines. So probably if we attach, we might be able to observe this kind of degradation low core count, but at that point, 3 cores is enough for any kind of performance. Yeah.
Do we have any more questions? OK, I do not see any, so thank you for attendance.
Thank you for coming. Yeah. Thank you.